started.
So the first one here is set up to make it really easy to solve using substitution. So I'm still going to label them equations A, B, and C. But as we look at this, we find that equation C is just one variable, 5x equals 20. So we can very quickly solve that to get x by dividing by 5. X equals 4. Now that we have that, we can go back into the next equation, the next one up, equation B, only has x and z. So if we know x, we can find z. So 2 times 4 instead of 2 times x plus 3z equals 5. 2 times 4 is 8 plus 3z equals 5. And then we'll solve by subtracting 8. 3z equals negative 3, and we'll divide by 3. Z equals negative 1. And then we have to find a, or find a y, going back to equation A. 3x is going to be 3 times 4, plus 2y, well, y is what we're looking for, minus 5z. Z is going to become negative 1. And now we solve. 3 times 4 is 12. Plus 2y. I'm going to treat this as a negative 5 times negative 1, which will be a positive 5, equals 11. 12 plus 5 is 17, plus 2y equals 11. Subtract the 17. We have 2y equals negative 6. We divide by 2. Y equals negative 3. So we get up here x equals 4 when y equals negative 3 and z equals negative 1. So that's it for that one. For number 2, it's a bit more complex than that. I'm going to label them equations A, B, and C again. This one, I suppose I could pretty easily solve for z here and use substitution. So there is one variable at least that would be easy to solve for. But as I look close, I see that the y column here, everything is lined up, x's, y's, z's, equals, and constants. The y column, we've got a 2y and a negative 2y, which will cancel out if we add them. And then we also have a negative y, which we can turn into a negative 2y pretty quickly. So we can get those to cancel. So the first thing I'm going to do is I'm going to combine B and C, because the 2y and the negative 2y will eliminate. So 2x plus 3x is 5x. 2y plus negative 2y cancels out. 3z plus z is 4z. And 4 plus 10 is 14. So there's one of my two variable equations in x and z. Now I haven't used equation A yet, so I have to use A, and I have to get rid of the variable y because that's what I got rid of before. What I'm going to do is this. I'm going to multiply equation A by 2. I'm going to write it up above here just to save space. 5x times 2 is 10x. Negative y times 2 is negative 2y. 2z plus 2 is 4z equals 13 times 2 is 26. And I am going to do the 2a plus b. So I'm going to add 10x plus 2x is 12x. Negative 2y and positive 2y cancels out. That's 0y. 4z plus 3z is 7z. 26 plus 4 is 30. There's my second two-variable system. Or two-variable equation for my two-variable system. Now the next step is going to be a lot harder. My least common multiple for x, it looks like it's going to be 60 for 5 and 12. For z, it's going to be 28. So I guess we're going to go for the 28. We'll multiply this equation by 7 to turn that into a 28. This equation down here, we're going to multiply by a negative 4. So it's a 28, but we want it to be a negative 28. Remember, one of them has to be positive, one of them has to be negative. I'm going to arbitrarily choose the bottom one to be the negative. Now we have 7 times 5x is 35x. 7 times 4z is 28z equals 7 times 14 is 98. Down here it's negative 4 times 12 is negative 48x. Negative 4 times z is a negative 28z equals negative 4 times 30 is a negative 120. And now we'll go ahead and add those columns. 35x and negative 48x is a negative 7x. 28z and negative 28z cancels out. Oops, it should be a negative 13x, shouldn't it? Yeah, 35 and a negative 48 is a negative 13x. Sorry about that. And our 98 and negative 120 that is a negative 22. So now we can solve for x. We'll divide by negative 13. X equals negative divided by negative is a positive. 22 divided by 13 is 1 and 9/13. Now we have to substitute that back up into one of the next equations. I'll put that into this equation here, the 5x plus 4z equals 14. And I'll solve that for z. So 5x becomes 5 times 1 and 9/13 plus 4z equals 14. Well, 5 times 1 and 9/13 is, oh, what is it? I believe it's 9 and 3/13 plus 4z equals 14. We'll subtract the 9 and 3/13 to get 4z equals 4 and 10/13. Now we divide by the 4. Z equals 1 and 5/26. Now we find y by going back to one of our original equations. Let's go back to this first one here. 5x minus y plus 2z equals 13. Now I'm going to pull from over here. I know that 5 times x is 9 and 3/13 minus y plus 2 times z is 1 and 5/26 equals 13. So I have to do 2 times 1 and 5/26. That is 2 and 5/13. I am going to add 9 and 3/13 and 2 and 5/13, which makes 11 and 8/13 minus y equals 13. I subtract 11 and 8/13. I get that negative y equals 1 and 5/13. And then, of course, I have to divide by the negative 1 to get rid of the negative. So y equals a negative 1 and 5/13. So we have x equals 1 and 9/13, when y equals a negative 1 and 5/13, and z equals 1 and 5/26. Any questions on either of those? Okay. Those are long processes, and when we get especially if we get a fraction for our answers, yeah, it's a lot of calculation and a lot of chances for mistakes. So today we're going to learn about a tool that helps us solve these electronically, makes it a little bit simpler to work with, and that's called a matrix. A matrix is just an organized set of numbers. If you dealt with computer programming, a matrix in computer programming is called an array. It's just a set of numbers where the position of the number within that structure tells you what it represents. We might have a matrix like this. First of all, a little bit about the matrix. These are the rows. This has 2 rows. We say that means R equals 2. And it has columns. Those are the columns. This has 3 columns, so we would say C equals 3. The dimensions of this matrix. Dimension is always row by column. So this is a 2 by 3 matrix. Now that is not a multiplication there. That's not saying 2 times 3. You're not getting a dimension of 6. It's 2 by 3. Now in a matrix, like I said, the position of the numbers means something. This number here, this negative 2, is in row 1, column 2. That means something. Every number that appears in row 1, column 2 of a matrix like this represents the same thing in the context. This might be a structural matrix for a beam or shear matrix for a wall. In engineering, matrices like this occur all the time. Well, what we are concerned about for this class, for this section of the class, is a special type of matrix called a square matrix. And in a square matrix, the number of rows equals the number of columns. By the way, these brackets are typical to put around a matrix. Little square brackets. So this is a square matrix because it is 2 by 2. 2 rows, 2 columns. This is a square matrix. 3 rows, 3 columns, 3 by 3. The reason a square matrix is special is because in the square matrix, we can calculate something called a determinant. And it can only be found for a square matrix. Unfortunately, the method for calculating a determinant varies depending on the size of the matrix. For a 2 by 2 matrix, there's a very simple way to calculate the determinant. But if they get bigger from a 2 by 2 matrix, the process gets to be more complex. For a 2 by 2 matrix, I just will use the same numbers I had up here, 3, 5, negative 2, 4. Now, first of all, those squared brackets like I have there are just signifying that this is a matrix. If those brackets look like this, they're straight brackets. Those brackets are saying find the determinant. We've seen those straight brackets like that before when we did absolute value earlier on. It's saying the absolute size of something. The absolute value of 7 was 7. Because whether it's positive or negative, it's still 7 units long. Now, excuse me, the determinant itself is then calculated. We do a down diagonal product. Which would just be like this, 3 times 4, which is 12. And from that we subtract the up diagonal product. Well, going up the diagonal would be this direction. Negative 2 times 5 is negative 10. So this is 12 minus a negative 10. Minus a negative, remember, is plus a positive. So the determinant of that matrix is a 22. So again, I have the straight brackets, which is telling me find the determinant of. Now I could just also say find the determinant of that matrix and use the regular matrix brackets. But when I do the straight ones, I don't have to say that. It's implied that we're finding the determinant. We do our down diagonal, 5 times 7, 35. Do our up diagonal, 2 times 1 is 2. And remember, it's the down diagonal minus the up diagonal. 35 minus 2 is 33 is our determinant. Now, a determinant can be 0. A determinant can be negative. It can be any value. But it comes in a 2 by 2 matrix. It comes from combining those two products, down diagonal and up diagonal. In your notes, I'm going to have you try one quick. Try that one quick. So 2, negative 3, 4, negative 5. So we do our down diagonal product. 2 times negative 5 is negative 10. Our up diagonal product, 4 times negative 3 is negative 12. So our determinant is the down product, negative 10, minus the up product of negative 12. Well, minus negative 12 becomes plus positive 12. Negative 10 plus a positive 12 is a 2, is our determinant of that matrix. When I get to a 3 by 3 matrix, there are 2 options. I'm going to show you the simplest option first. So again, I'm using the straight brackets, which implies that we're finding a determinant. So if I have a 3 by 3 determinant, I'm going to label my columns here A, B, and C. The reason for that is to start off my calculation here, the first thing I have to do is rewrite some columns. And let me explain why before I actually do it. Because I do a down diagonal product here, 3, 4, 1. If I do an up diagonal product, that'd be 3, 4, and 5. Notice there are 4 numbers that are left out if I do that. So when we use a 3 by 3 matrix, we do a down diagonal product for every entry in the top row. So we have the 3, 4, 1. That's the first one. Well, we have an entry, the 1, we go down that one. That would be 1, negative 2. And what actually happens is we wrap around, we go to the other side, and that's 1 times negative 2 times 3. Well, to avoid confusion there, what we do is we just rewrite the first 2 rows. We do 3, 2, and 3. That's row A is rewritten. And we do row B again, 1, 4, and 4. So now when we do our down diagonal products, we just go down the diagonals. We don't have to wrap around. We have those numbers already there. So 3 times 4 times 1 is 12. 1 times negative 2 times 3, that's a negative 6. And 5 times 2 times 4 is a positive 40. To get the total down diagonal product, we add those together. So 12 plus negative 6 is 6, plus 40 is 46. That's my down diagonal product, total down diagonal product. Notice I caught every number in the matrix with those down diagonals. Now I'm going to do my up diagonals, and I'll catch every number in the matrix as well. 3 times 4 times 5 is 60. 4 times 2 times negative 3 is a negative 24. And 1 times 2 times 1 is a 2. Well, 60 plus negative 24 is 36, plus 2 is 38. That is my total up diagonal product. So my determinant is my down diagonal product, the 46, minus the up diagonal product, the 38. 46 minus 38 is 8. So my determinant of this matrix is 8. If I ask you to do a determinant of 2, 1, negative 3, 5, 2, 4, and 3, 0, 2. Once again, I'm going to start off by rewriting those first 2 columns. We're at 2, 5, 3. That's the first column copied over. And then 1, 2, 0 would be the second column copied over. And now I will do my down diagonal products. 2 times 2 times 2 is 8. 1 times 4 times 3 is 12. And this row, this diagonal, there's a 0 in it, which means I don't have to worry about the other numbers. If there's 3 numbers multiplied together, if one of them is a 0, the product is 0, no matter what. So 8 plus 12 plus 0 is 20. So I have 20 for my total down diagonal product. Going up, I have 3 times 2 times negative 3, which is negative 18. So 0, 4, and 2, once again, there's a 0 in it, so that's a 0. 2, 5, and 1, which is 10. We add those, negative 18 plus 10 is a negative 8. And now we have 20 minus a negative 8, which of course is the same as 20 plus a positive 8. 20 plus 8 is 28. So that matrix has a determinant of 28. I'm going to have you try one in your notes.
I'm sorry, what was the determinant for that top one?
28, or for the other one? I had 28 for this one and 8 for the one before that.
Okay, all right, thank you.
You bet. So for this one, I'll give you a couple minutes, see what you come up with for the determinant. So we'll recopy our first two columns. So we've got 2, 1, 5, 3, 4, and 2. Doing my down diagonal products, I have 2 times 4 times negative 1. That's negative 8. 3 times 1 times 5, that's 15. 2 times 1 times 2 is 4. That adds together to make 11. Negative 8 plus 15 plus 4. Going up, I have 5 times 4 times 20, which is 40. Or sorry, 5 times 4 times 2, which is 40. 2 times 2, or 2 times 1 times 2, which is 4. And negative 1 times 3, which is a negative 3, which adds up to 41. So this determinant is 11 minus 41, which is a negative 30. So that's all the material for the first hour. There's a worksheet on Blackboard labeled determinants and matrices, or matrices and determinants. That's going to be our homework. But rather than give you some homework time and take a break, I'm just going to push on because there's only about 25 or 30 more minutes of material, so we'll get you guys done. So what I want to start looking at is something called a cofactor. Well, there's two things. I want to define a cofactor, and I'm going to define a minor. A cofactor and a minor are both properties of a single entry in our matrix. So if I look at a matrix, like 5, 1, 3, 2, 7, 4, 3, negative 2, 1. It's a 3 by 3 matrix. And really, the cofactor and minor only really have meaning in a square matrix. They're defined in other matrices, but it really is only helpful in a square matrix. So let's take the value here. Let's do the 4. The cofactor is the row plus the column of that number. So for the 4, that's in row 2. Column 3, that's 5. If that number were positive, the cofactor would just be the entry. In other words, it would just be 4. Or sorry, not positive, I should say even. R plus C is even. Then it's just the entry. It's the positive of the entry, or whatever the entry is. If that cofactor is odd, then it is -1 times the entry. Well, here it is odd. 2 plus 3 makes 5. That 4 is in an odd location, which means the cofactor of the 4 in that location equals -1 times 4, or -4. So that entry has a cofactor of -4. The minor excludes the row and column of the entry. And this will give us a 2 by 2 matrix. Or a matrix one dimension smaller than the one we're working with. If we were working with a 4 by 4 matrix, the minor would be a 3 by 3 matrix. So here our cofactor, remember we said it excludes the row and the column. So the row that's in is the 2, 7, 4. It excludes that row. And it excludes this third column, the 3, 4, 1. What's left? Well, we have 5, 1 and 3, -2. That 2 by 2 matrix is the minor of the entry 4. So in this matrix, I would like you to find, for the 3, cofactor and minor. And then also for the 5, find the cofactor and minor. So for the 3, it's in row 3, column 3. So 3 plus 3 equals 6, which is even. Which means the cofactor, it's actually a -3. It's just the entry. The entry is a -3. The cofactor is just the entry, -3. So it stays a -3. The minor, we're going to exclude its row and column. The minor, we have 7, 3, 5, -2. There's the minor. For the 5, it is in row 2, column 1. 2 plus 1 is 3. That is an odd number. So our cofactor is -1 times that entry of 5, so it's a -5. The minor, well, exclude that row and that column. We're left with a minor of 3, 1 and 4, -3. Any questions as to how I got the cofactor and minor for either of those entries? Okay. So the question is, why do we care about a cofactor and minor? Well, you recall I said there are two main ways of finding the determinant for a 3 by 3 matrix. One of those is by using partials. A partial is equal to the cofactor times the determinant of the minor. And what we do to find a determinant using partials is we pick a row or column to expand about. Let me show you what I mean. So I'm going to take a matrix here. 3, 5, 2, 4, negative 1, 3, 2, 1, 5. So there is my matrix. I can pick any row or any column to expand this about to find its determinant. I'm going to pick row 1. So I'm going to expand around row 1. Well, in row 1, I have the entry. First one is 3. Its cofactor. Well, that's in row 1, column 1. That's a 2. This is even. The cofactor is just 3. It's just the entry. The minor, if I cross out the row and column for the 3, is negative 1, 3, 1, 5. Now I'm going to need the determinant of that, so I do my down diagonal. Negative 1 times 5 is negative 5. My up diagonal, 1 times 3 is 3, so negative 5 minus 3 is a negative 8. So my expansion is that partial. Cofactor times the determinant of the minor. 3 times negative 8 is a negative 24. Is the expansion for that term. Now I still need to do the next term. Need to expand now around the entry of a 5. Well, that 5 is in row 1, column 2, which adds up to 3. That's odd. So negative 1 times the entry, or negative 1 times 5, gives us a cofactor of negative 5. A minor there, if I cross out that row and that column, is 4, 3, 2, 5. And I find that determinant. 4 times 5 is 20. 2 times 3 is 6. 20 minus 6 is a 14. So the expansion negative 5 times 14 is a negative 70. And I have one more entry in that row, which is the 2. The 2 is in row 1, column 3, which adds up to 4. That's an even number. So it's just the entry. The cofactor there is just the 2. Its minor is 4, negative 1, 2, 1. That's just taking out the row and column of the 2. That 4 times 1 is 4. 2 times negative 1 is negative 2. So 4 minus a negative 2 is 6. And so the partial for that is 2 times 6 is a positive 12. And I'm going to add those three numbers. Negative 24 plus negative 70 is a negative 94. Plus 12 is a negative 82. That gives me a determinant of negative 82. Well, you might be thinking, but why did I choose the top row? There really wasn't a good reason. So let's take that same matrix, 3, 5, 2. Four, negative 1, 3. And 2, 1, 5. And let's find its determinant using a different row or column. Remember, we could pick a row or a column. Let's pick a column. Let's do the second column. So our first entry in that column is the 5. Its cofactor. Well, it's row 1, column 2. That adds up to 3, so that's going to be a negative 5. Notice when we had the 5 in the top row, it was a negative 5 as well. The cofactor of that entry is always going to be the same, no matter whether we're picking a row or a column. That 5 up there is always going to have a cofactor of negative 5 in that position. It's minor. Will be 4, 3, 2, and 5. That's just removing its row and column. We do the determinant of that minor. 4 times 5 is 20. 2 times 3 is 6. 20 minus 6 is 14. Negative 5 times 14 is a negative 70. My next entry is the negative 1. It is in row 2, column 2, which adds up to 4. That's even, so it's just the entry, but that's already a negative 1, so it stays negative 1. My minor, I'll remove its row and its column, is going to be 3, 2, 2, 5. I find that determinant. 3 times 5 is 15. 2 times 2 is 4. 15 minus 4 is 11. That expansion there, negative 1 times 11 is negative 11. My last entry to expand about is the 1 on bottom. It is in row 3, column 2, which adds up to 5. That's odd, so that's a negative 1 cofactor. Its minor, if I take out its row and the column, is going to be 3, 2, 4, 3. So I do that determinant. 3 times 3 is 9. 4 times 2 is 8. 9 minus 8 gives us a determinant of 1. So that partial is negative 1 times 1 is a negative 1. I add up those three. I once again get negative 72. So it does not matter which row I expand about or which column I expand about. The determinant here, you can see, came out to be 72, negative 72. Oops, not negative 72, negative 82. Helps if I add correctly. Negative 82 both times. So I get the same determinant if I add correctly, no matter which row or column I expand about. So you might wonder, why is this a big deal? Why are we bothering to learn this? This looks a lot more complicated. The reason why we are learning this expansion with partials and the cofactors and minors is because if we get larger than 3 by 3, that's the only way we can do a determinant of a matrix. At 4 by 4 and larger, the diagonal method does not work. Now, we can make life a lot easier on ourselves when we use this method. When we choose a row or column to expand about, by choosing one that makes life easier. For example, let's say a 5, 9, 0, 3, negative 7, 2, 6, 5, 0. These have some little bit larger numbers, not really large, but it's going to give us some bigger results than what we've been getting so far. We could do the diagonal method, but we'd be working with a lot of those big numbers. If we were to expand using those partials and minors, and if we use this last column, well, our entry here, first entry is 0. Well, guess what? The cofactor of that doesn't matter its position. It is in row 1, column 3, which is even, but even if it was in an odd spot, negative 1 times 0 is still 0. So the cofactor of a 0 is always going to be 0. And it doesn't matter what its minor is. I mean, it has a minor, we could find it, and we could find its determinant, but we're going to take that determinant times the cofactor is 0. That partial is 0 no matter what, if the entry is 0. We have this entry of 2. That is in row 2, column 3. That is 5, which is odd, which means that cofactor is negative 1 times the entry. That's a negative 2. It's partial, and we take out its row and column, or sorry, it's minor. We take out its row and column, we 5, 9, 6, 5. So 5 times 5 is 25. 6 times 9 is 54. 25 minus 54 is a negative 29. We multiply, negative 2 times a negative 29 is a positive 58. The next entry is 0 again. So no matter what, its cofactor will be 0, and it doesn't matter what the determinant of its minor is. We multiply by 0, it's going to be 0. So the determinant of this matrix is just that 58. What's going on here? There we go. It's just that 58 because that was the only non-zero entry in that column. So if we pick columns or rows that have a lot of zeros in them, we can save ourselves work because the zeros, the expansion of a 0 is going to be 0. It's going to give us a partial of 0 no matter what. Let's just take a peek at a 4x4 matrix. So I'm trying to find the determinant of this matrix. I am going to choose this third row to expand about. The reason is there's 2 zeros there. So that's 2 terms. I don't even have to bother to expand. So my entry, I'm not even going to do the entry, and I'll do the cofactor together. For the 2, that is in row 3, column 1, so that adds up to 4. So that's just a cofactor of 2. That's even, so it's just the entry. Our minor, we exclude its row and its column. You'll notice here that the minor is 3 by 3. 2, 3, 7, 3, 5, 1, 2, 4, 3. Now, we could expand that with minors if we wanted to, but I don't want to. I'm just going to add the columns. I'll do the diagonal method here. 2 times 5 times 3 is 30. 3 times 1 times 2 is 6. 7 times 3 times 4 is 84, which is 120. Going up, 2 times 5 times 7 is 70. 4 times 1 times 2 is 8, and 3 times 3 times 3 is 27. That's a 105. That's 120 minus a 105 is a 15, is the determinant of our minor. So we have a cofactor of 2 times a determinant of our minor of 15 gives us a 30 for the partial for that term. Now, we don't need to expand around that 0 because it's just going to give us a 0. So we'll do this 1. That's an entry of 1. It is in row 3, column 3, which adds up to 6, which means our cofactor is just the 1. We cross out it, we ignore its row and column to get a partial, or sorry, a minor. So 527, 631, 323. And we will do that determinant. Five times 3 times 3 is 45. 2 times 1 times 3 is 6. 7 times 5 times 2 is 70, which adds up to 121. Going up, 3 times 3 times 9, 3 times 3 times 7 is 63, plus 2 times 1 times 6 is 12, plus 3 times 5 times 2 is 30, is 105. We have 121 minus 105 is a 16. So, to complete our partial there, we have 1 times 16 is 16. For the next entry, it's a 0, so we don't need to do that entry. So all we have for our determinant is 30 plus 16 is 46. Now, luckily, we're not required, I'm not going to require you to do a determinant of a 4x4 matrix in here. I might give you an extra credit question where I ask you to break down, do the determinant of a 5x5 matrix. If I ask you to do the determinant of a 5x5 matrix, you have to pick a row or a column to expand around. It really doesn't make a difference here. I'll pick that third row. To expand around the 1, its entry is 1, its cofactor, it's row 1, column, or row 3, column 1. Its cofactor is a 1. Its minor, however, take out the row and column, its minor, 721 negative 4, 3521, negative 1432, 2143. Its minor is a 4x4 matrix. We need to find the determinant of the minor. Guess what? That would mean you'd have to go back up and do this process, expand that 4x4 matrix to find its determinant of that minor. Then you'd come back, put that number in here to do the expansion for that term. There are 5 items in each row or column here, which means we'd have to do 5 of these minors. Each of those minors would have to have 4 items in each row or column. So that would be 4 3x3 matrices. To do a 5x5 matrix, you have to have 20 3x3 matrices. That's why it would be an extra credit question. I will put it out there for the end of the semester if you guys want to do an extra credit question, by the way. Okay, so with that, I have actually covered everything we have. So you have that worksheet posted in there for today. Matrices and determinants. Also, there's a quiz out there on 3-variable systems. So we have about 37, 38 minutes left. That should be your homework time and your time for doing that quiz for both hours of class here. I will be on the network to answer any questions if you'd like to start on any of that. Otherwise, if you want to